everyone. Good afternoon. Students, am I audible and visible? Give your answers in the poll which I have launched. Just let me know if I'm visible and audible. Good afternoon, Febia. Good afternoon, Roshan, Bangtoy, and the one who is watching from JNBID. Am I visible and audible to all of you? Am I not audible? Can you able to hear my voice? Yes. Okay. Fine. So let's start with the today's session. Okay. So we are dealing with the thermodynamics. Am I not visible, students? Can you able to see me and hear me? Let me know your answer in the chat box. Am I not visible? Roshan, can you tell me whether I'm visible and audible or not? Bangtoy, can you let me know? Hello. Students, can you able to see me? Students, am I audible and visible now? Is it okay? All of you can able to see the screen and all of you can able to see me and all of you can able to hear my voice, right? Trisha, Sanjana, Roshan, Fibia, can you give a reply over there in the chat box? Say yes or no if I'm visible and audible. Okay, fine. So let me start with the session. Yeah, thank you, Sanjana. So yesterday we have discussed some of the basics of thermodynamics and some terminologies also we have discussed, right? And we have discussed the first law of thermodynamics, etc., and some related concepts. So today we are going into a new topic which is called as Hess's law, okay, or Hess law we can say. So here the topics that we are going to cover under Hess law are thermochemical equation and Hess summation law. Okay. So let's start with the thermochemical equation. So before moving on to the equation, we are going to study some terms. So the first term is the enthalpy of the reaction. So the definition says that it is the energy change accompanying a reaction. Okay. Energy change accompanying a reaction is called as enthalpy of reaction. So for example, I am going to take a reaction in which the reactant is going to give me the product. Okay. And to be more specific, I'm having two reactants, A and B. AA plus BB is giving CC plus DD moles of product. So this is a reaction. So now what is the enthalpy change or the energy change accompanying this particular reaction? So that is denoted by the letter delta HR. It is denoted by the letter delta HR and we call this as enthalpy of the reaction. So this delta HR will be equal to sum of enthalpies of products minus sum of enthalpies of the reactants. Okay, so who are the products here? C and D are the products. And A and B are the reactants. So first of all, we have to take the enthalpies of product with the stoichiometric coefficient. And then we have to take the enthalpies of the reactants with their stoichiometric coefficient A and B. So to find out the delta HR, you are going to memorize a formula. And the formula says that it is the sum of enthalpies of product minus reactants. Okay, it is product minus reactant. Clear for all of you? So this is the enthalpy of reaction. The formula is very important. Okay, so I can write this in a simplified manner. Delta HR is equal to sum of the enthalpies of delta H of the products minus sum of means summation. Okay, if I write like this, it denotes the summation. So enthalpies of the reactant. So product minus reactant will give you the enthalpy of the reaction. Okay, so now let's move on to standard enthalpy of reaction. So in the previous slide, we have discussed about enthalpy of reaction. This is about the standard enthalpy. So the enthalpy change for a reaction when all the substances are in standard state is called as standard enthalpy of reaction. Okay. So I will give you the standard states later on. Now let me give the notation we use for standard enthalpy of reaction. So it is denoted by delta HR naught. So the zero which we are putting in the superscript denotes the standard. Okay. The zero which we are putting in the superscript denotes the standard value. So delta HR naught means standard enthalpy of the reaction. Okay. And the standard conditions. So what are the standard conditions? So for temperature and pressure, we have the standard value. So the standard temperature will be 298 Kelvin and the standard pressure value will be 1 bar pressure. Okay. So if I take the standard state of ethanol, it is at 298 Kelvin and 1 bar pressure means it is a pure liquid ethanol. Okay. The standard state of ethanol at 298 Kelvin and 1 bar pressure is pure liquid ethanol. Clear? So this is all about delta HR naught. Okay. And one more thing I'm going to say, the standard enthalpy of formation. So first of all, we have discussed the enthalpy of reaction. Then secondly, standard enthalpy of reaction. Then in the third case, it is standard enthalpy of formation. So this is very, very important. Standard enthalpy of formation is very, very important. So what it is? It is the enthalpy change for the formation of 1 mole of the compound. Okay. 1 mole of the compound from elements in their most stable state. Most stable state is also called as reference state. It is also called as native state. Okay. So, for example, if I take oxygen, oxygen is present in its gaseous form in the atmosphere, right? So, that is a gaseous form is the native state of oxygen. Okay. So, that particular native state is called as the most stable state or the reference state. So, 1 mole of the compound should form from its constituent elements in their most stable state. And it is denoted by delta HF naught. It is denoted by delta HF naught. Now I'll give you the standard form of some elements. Okay. So here are the standard form of some elements. So first of all, carbon. So carbon in the graphite form is the standard form of carbon. So we do have some other allotropes of carbon, right? Like we have diamond, we have graphite, we have fullerene, we have graphene. So all these are the allotropes of carbon. But the standard state of carbon is graphite, not diamond, or it is not fullerene, etc. Okay. And next to the standard state of bromine is liquid. So bromine standard state is liquid form. And oxygen, I have already told you, the gaseous form is the solid form of, standard form of oxygen. And coming to iodine, iodine standard state is solid. Iodine will be in the solid form. And nitrogen, you all know, it is a gas. And coming to phosphorus, we have red phosphorus, white phosphorus, and black phosphorus. So out of three, red phosphorus is the standard form of the phosphorus. Okay. And also we have mercury in the liquid form and sulfur in the rhombic state. Okay. The rhombic form of sulfur is the standard form of sulfur. So these are some of the most common elements and their standard state. So you need to memorize this table. Clear? So now we will see some examples according to this definition, and we will see whether the delta HF naught applies to the equation which we are going to see. Okay. So first example is calcium oxide reacting with carbon dioxide to give calcium carbonate. So here the delta H R naught is written for this equation. Delta H R naught is given for this equation. Why delta H R naught? Why not delta H F naught? Can anyone give me the answer for this? You can read the definition once and you can let me know why delta HF naught is not written for this equation. Let me see who is going to give me the answer. Why delta HF naught cannot be written for this formula? Any idea for anyone? So here, according to the definition, if you see, because it is enthalpy of the reaction. Yes, Roshan, it is enthalpy of the reaction. But why not delta HF naught? Why we are not able to write the delta HF naught for this reaction? We can able to write delta HR naught, right? Why can't we write delta HF naught for this reaction? Why it is not the standard enthalpy of formation? I'll give you the reason. So listen carefully. 1 mole of the compound should form. Yeah, 1 mole of calcium carbonate has formed. So it is correct. And that 1 mole has to come from the elements. So how many elements we have here and what are they? We have calcium, we have carbon, we have oxygen. So what is the standard state of calcium? Calcium will be in the solid form, carbon will be in the graphite form, and oxygen should be in the gaseous form. So these three elements should present as a reactant. But instead of these three, we have calcium oxide, which is a compound It is not an element. It is a compound. And carbon dioxide also is a compound. It is not an element. So, 1 mole of the calcium carbonate has formed, but not from their constituent element, but from different compounds. It has been formed from different compounds. So that's why we cannot able to write the standard enthalpy of formation. Okay, calcium carbonate is not formed from the constituent elements, but it has been formed from some other compound. Now it is clear for all of you. Do any of you have doubts here in this concept? Roshan, it is okay now. Students, can you able to understand? If you can able to understand, please type yes in the chat box or give me a thumbs up. Okay, daily, every day I'm saying you guys are keeping so quiet. I don't know why. Huh? Yes. Let's go for one more example. So this is hydrogen reacting with bromine to give to HBr. And for this reaction also delta HF naught is not given. Only delta HR naught can be written. Why? Can you think of it? So we have hydrogen and bromine. So the hydrogen standard state is gas and the bromine standard state is liquid. Okay, so we have those two in the reactant. But why delta HF naught is not given for this reaction? What could be the reason? Very easy to answer this. So go through the definition, all of you. Very good, Sanjana. You are correct. So enthalpy change for the formation of 1 mole of the compound formed. Okay. So here the compound formed is 2 moles. So even though the compound has been formed from their constituent elements, 2 moles of the compound has formed. So we cannot write the delta HF naught. Okay. So it is not the standard enthalpy of formation because 2 moles of the compound is formed instead of 1 mole. Clear? So I hope it is clear to all of you. So shall we go for one question? Shall we go for one question from the topics that we have seen so far? So I'll move on to the question. Here is the question. Enthalpy of formation of carbon monoxide, carbon dioxide, N2O, N2O4 are given. Find the delta HR for the reaction. Reaction is also given to us. So how we need to solve this question? We need to find out delta HR. So what is the formula we have studied? What is the formula we have studied? Delta HR is equal to summation of delta HF naught of product minus delta HF naught of the reactant. So this is the formula we have studied, right? Product minus reactant. So we have the values for all the 4 compounds. Here we have the values, right? 110, 393, 81 and 9.7. So we have the value, enthalpy of formation value for all the 4 compounds. So we have to just apply all the values here. So first of all, go for the product. So we have N2O and carbon dioxide. But we have 3 moles of carbon dioxide. So while substituting, what you have to do? You have to multiply the delta HF naught of carbon dioxide by 3. Okay, in the same way, minus, we have 3 moles of carbon dioxide. So 3 into this CO and 1 into N2O4. So substituting all the values, we will get minus 777.7 kilojoule per mole as the answer for delta HR. Okay. Is it clear for all of you? You just need to memorize this formula. To find out the standard enthalpy of reaction from standard enthalpy of formation, you need to do product minus reactant. Okay? Product minus reactant. So all of you please note down this formula. This is the formula to find out the standard enthalpy of reaction from the standard enthalpies of formation. Have you all taken this down in your notebook? Shall I go for the next topic? Yes. Shall I go ahead, students? Yes or no? Yes. Okay. So the next topic is Hess summation law. So we are going to study what is Hess law. So it states that regardless of the multiple stages or steps of a reaction, the total enthalpy change for the reaction is the sum of all changes. So a reaction can go in a single step or it can take multiple steps. Okay. So the total enthalpy change for a particular reaction is the sum of all the changes. So let me take this. I have a reactant A and A is getting converted to product. And the enthalpy change accompanying this process is delta H. So A can directly go to B and also it can take multiple steps to reach the B, right? So this is the total enthalpy change and that is equal to the steps, sum of all the changes. So A to C, C to D and D to B. So this is the path number 2. This is path 1 and this is path 2. So if I add all the delta H values of path 2, that will be equal to the delta H value of path 1. Okay, this is Hess law. Very easy. Okay. So now let me summarize the topics that we have discussed. So first of all, we have learned the enthalpy of reaction and also the formula to find out the standard enthalpy of reaction and enthalpy of reaction, and the standard enthalpy of reaction means the conditions are 298 Kelvin and 1 bar pressure. Then coming to the standard enthalpy of formation, it is the 1 mole of compound formed from its constituent elements. This is very important. From its constituent elements in their most stable state. All right. So this is all about the Hess law. Now the next topic is thermochemistry, and this is the second half of this lesson. Okay. So far we have discussed the thermodynamics part of this lesson. Now we are getting into the thermochemistry. Okay, actually this lesson is divided into two, but a single name is given for this lesson, which is thermodynamics. But also we have the second half with the name thermochemistry. So this is more specific name for this concept. Okay. So the learning objectives under thermochemistry are standard enthalpy of combustion, enthalpy of atomization, and bond enthalpy. And we are going to study the definition for lattice energy and hydration enthalpy. So everything deals with the enthalpy here. Okay. Thermochemistry. So what is the first topic? Standard enthalpy of combustion. Standard enthalpy of combustion. So what it is? How to denote this standard enthalpy of combustion? It is denoted by delta H C naught. Delta H C naught. So can anyone give me the definition for combustion? I will move on to the definition for standard enthalpy of combustion later. So before that, can anyone give me the definition for combustion? What is combustion? What is combustion, students? In your 10th class, you might have studied, no, the definition for combustion or some of the concepts which related to this combustion. Combustion is heating something in presence of oxygen. Okay. Combustion is heating something. Yeah, burning of the molecules in presence of oxygen. Very good, Tanuja. Very good. Tanuja is from which JNB? Tanuja ST. May I know your place?
JNV Gadag.
JNB Gadag. Okay, good, good, great. Very good. Your answer is correct. So burning of a molecule in presence of oxygen is called as combustion. Okay. So now, what is standard enthalpy of combustion? The enthalpy change when 1 mole of substance is completely burnt in presence of sufficient supply of oxygen. Definition is same. Only one thing is added. So the enthalpy change when 1 mole of the substance is undergoing this process. Okay. And we do have some points to note down. The first point that you have to look into is all the reactants and all the products should be in the standard state. Okay. If I want to write the delta HC not for any reaction, then all the reactants and products should be in the standard state for that reaction. Okay, you all know what is a standard state, right? So the pressure should be 1 atmospheric pressure. Pressure is 1 atmospheric pressure and the temperature is 298 Kelvin. Temperature is 298 Kelvin. So I will give you one example. So this is one example. Okay. So C4H10 is called as butane. Butane is a gas and it is taking 6.5 moles of oxygen and it is getting converted to carbon dioxide and water. Okay. And delta HC naught can be written for this reaction because all the reactants, the butane and the oxygen, both of them are present in their standard state, which is the gaseous state. Okay, oxygen is also a gas, butane is also a gas. The pressure, temperature followed here is 1 atm and 298 Kelvin. Got it? And also the substance butane is present in 1 mole. So 1 mole of this butane substance is completely burnt. Okay. So how do we know that the butane has completely burnt with the oxygen? Just by looking into the products. Okay. So in the product side, if you are having carbon dioxide and water, then it means the particular substance has undergone complete combustion. If there is some incomplete combustion has happened for any substance, then the product would not be carbon dioxide or water. It would be some other elements. So it can be a carbon, okay? It can be a carbon or we may get carbon monoxide. So instead of carbon dioxide and water, if you get any other compound or any other element as a product, then it shows that the given substance did not undergo complete combustion. So those reactions are actually incomplete combustion reaction. Okay. Is it clear for all of you? For complete combustion, you should get carbon dioxide and water as a product. All right. So shall we go for the next term? Are you all okay with the standard enthalpy of combustion? Do you have any doubts from this? Students, 11th standard students, I'm talking with you guys. Do you have any doubt? Okay, thank you so much, student. Thank you, thank you, thank you. Very good. Kumar, Manish, good afternoon to both of you. You guys have joined late, it seems. JNV Kurnul also late. Huh? Okay, no problem. So try to be on time, okay? Try to join the class on time so that you will not miss the concepts. Fine. Now let's go for the next term, which is standard enthalpy of atomization. It is denoted by delta H A naught. Delta H A naught. So what is this? It is the enthalpy change for the conversion of 1 mole of any substance into individual gaseous atoms. I may have a compound or I may have a molecule. Okay, I should take only 1 mole of any molecule, 1 mole of substance. If I break the bond, the molecule will be broken down and it will form an atom, right? So the energy change or the enthalpy change accompanying that particular process is called as standard enthalpy of atomization. Okay, the conversion of a molecule into an atom. That's it. So here the condition is the product should be in the gaseous state. Who should be in the gaseous state? The products should be in the gaseous state. And this process is an endothermic process. What is meant by endothermic process? Energy absorbing or energy releasing? What is meant by endothermic? It is an energy absorbing process or energy releasing process, students? Very good. It is an energy absorbing process. Very good. Very good, Manish, Tanuja, and Kunal students. So, if the energy is getting absorbed, then what will be the sign of delta H? Yes, Sanjana. What will be the sign of delta H? If the energy is getting absorbed, what will be the sign? Yesterday we have studied, no? The sign convention for delta H. If the energy is absorbed, delta H sign will be positive. Very good. Very good. Yes. Delta H value will be positive. Now let's go with one example. Hydrogen. So we have a hydrogen molecule. Okay. So we have a hydrogen molecule. So one hydrogen atom is bonded with another hydrogen atom using a covalent bond. And if I break this bond, some amount of energy is required for this, right? Then only the hydrogen bond will be broken down. And that hydrogen molecule will absorb some energy. It will absorb plus 435 kilojoule per mole of energy, and it will be converted to 2 hydrogen atom. It will be converted to 2 hydrogen atom. Okay, so the energy that is getting absorbed by this hydrogen molecule to get converted into 2 atoms is called as standard enthalpy of atomization. Okay, you see the product is present in its gaseous state. So this particular point is also applicable. Okay. Can you all able to understand? Shall we go for the next term? Any doubt in standard enthalpy of atomization? Clear, right? The next is, okay, very good. The next term is bond enthalpy. So it is denoted by delta H bond naught. So can anyone give me the definition for bond enthalpy? Already in the periodic table lesson when I was teaching, I have said the definition for this bond enthalpy. What is bond enthalpy? The energy required to break 1 mole bond. Very good. Very good, Jainvi Kunal. So the energy observed in breaking 1 mole bond in gaseous phase is called as bond enthalpy. Let us take one example. Let me take a chlorine molecule. Okay. So here I have a chlorine molecule. Cl bond Cl. Okay. So I have a bond here. So if I want to break this bond, I have to supply some energy, right? I have to supply some energy so that the chlorine molecule will be converted to chlorine atom. And the reactant should be present in the gaseous form. Yes, it is present in its gaseous form. And it has got converted to chlorine atom. The energy changes 242 kilojoule. The bond breaking process is always endothermic. Okay, all of you please write down this in your notebook. The bond breaking process is always endothermic. Means if I want to break a bond, I should give some energy. Okay, so energy is observed. Energy is observed. Okay, and the process is endothermic. Delta H value will be positive. Here also you see we have a positive value, 242 kilojoule per mole. Okay, all the reactants and products should be in the gaseous state for this bond enthalpy. Bond breaking is a endothermic process, means energy is observed. Okay, so have you all noted this? And bond formation is an exothermic process. If a bond is forming between two atoms, energy will be released. So the process is exothermic in nature. Okay. So shall I move on to the next slide? All the reactants and products should be in the gaseous state for bond enthalpy. Clear? Yes. Now, next is the enthalpy of reaction in terms of bond energy. So how to write delta HR from the bond energy values? So I have a reaction CH4 plus 4Cl2 giving CCl4 and HCl. Okay, CH4 plus 4Cl2 is giving CCl4 and HCl. So bond is broken down in the reactant and it is formed in the product. Okay. So now for this particular reaction, I want to write the delta HR naught from the bond enthalpy. So here the formula is the bond and summation of bond enthalpy of reactant minus summation of bond enthalpies of product. Previously, we have studied one formula similar to this, no? What was that? We have found out the standard enthalpy of reaction from enthalpy of formation. So from enthalpy of formation, if you want to find out delta HR, you need to do product minus reactant. Okay. But here it is reactant minus product. From delta HF naught, if you want to do, you have to do product minus reactant. Now, from the bond enthalpy, if you want to find out, you have to do the reactant minus product. Okay, just a small difference. Okay, just a small difference you need to keep in your mind. All the substance should be in the gaseous state. If something is there in the solid form, then you should not consider the bond enthalpy value of that particular compound. Or if something is in liquid form, you should not consider for that also. Clear? So please note down this formula, which is very important. Any doubts so far till now for anyone? From the thermochemical equation, from Hess law, and from the standard enthalpies of combustion, atomization, and bond enthalpy, everything is clear? Only the formulas we are going to study, okay? Nothing much. So you need to keep some points under each topic in your mind and nothing much to memorize. Okay. So just Now here and there some formulas you need to memorize and some points like this. So for this all the substance should be in the gaseous state, right? So accordingly for some other things you need to study the standard state of some elements like that. Shall I go for the next topic? The next is lattice energy and hydration enthalpy. So let me go first with the lattice energy and later on we will study what is hydration enthalpy. So it is denoted by delta H of lattice. What is the definition? The energy required to break 1 mole of ionic compound. Energy required to break 1 mole of ionic compound in solid form, in solid state to form free gaseous ions. So I have to take an ionic compound. I have to take an ionic compound. For example, we can take NaCl. NaCl is an ionic compound, right? I have to take this NaCl. I have to take 1 mole of this NaCl and it should be present in its solid state. Okay, so let me take the reaction. So here you see 1 mole of the NaCl is taken in its solid state and it is forming the free gaseous ions. Na plus ion, Cl minus ion. Ions means cation and anion. Okay, so both the ions are present in their gaseous state. Okay, so for this particular reaction, energy is required, right? So I need some energy to break this NaCl bond and that bond energy is called as lattice energy. So why it is called as lattice? So NaCl lattice means it will have more number of Na plus ion and more number of Cl minus ion. Not only one Na and one Cl. In 1 mole of the compound, we have Avogadro number of particles of that compound, right? So this is the lattice of ionic compound NaCl. After absorbing some amount of energy, the bond between the sodium and chlorine, the purple color atoms are sodium and the green color atoms are chlorine. So the bond which is present between the two ions will be broken down. Okay. And it will lead to the formation of cations and anions. Free gaseous cation and anion. Okay. Clear? I will give you the value also. It is plus 787. Plus means it is an energy absorbing process. Okay, endothermic. Because the bond is broken down, right? I already told you bond breaking is an endothermic process because energy is absorbed to break a bond. Okay. So now let us see the difference between energy absorption process and the energy releasing process. Okay, so we'll start with the energy absorption thing first. If the energy is getting absorbed for any reaction, then the definition we are giving for such processes, the 1 mole of ionic compound gives its constituent gaseous energy. This is an energy absorbing process. And here, all the ionic bonds are broken. Bond breaking process. Energy absorption means it is a bond breaking process. And the example is NaCl giving Na plus and Cl minus. Okay. And the delta H value will be positive here in this endothermic process. So this is an endothermic process. You can note down this also. It is an endothermic process. Okay. And coming to the next one, energy releasing process. This is exothermic. Energy releasing means exothermic process. So here what will happen? Gaseous ions gives 1 mole of ionic compound. Gaseous ions will give. Ions will join together and they will form a compound. So the bond formation occurs. Ionic bonds are formed here. So this is an example, just the reverse of this reaction. Na plus Cl minus gives NaCl. Okay, the bond is formed between the sodium and chlorine. And here delta H will be negative. All right. So if you want to write this down in your notebook, you can take it. Finished? Shall we go for the next? Okay. The next is hydration enthalpy, which is denoted by delta H hydration naught. Okay. So here, this is the enthalpy change when 1 mole of a substance or ion is completely hydrated by water. So I have to take an ion. Okay, the ion should be the free gaseous ion. Okay, I will give you the example. So Na plus ion I am taking, sodium ion. Okay, it is in its gaseous form and it is present in its 1 mole. And with this, X moles of H2O is reacting. X moles of H2O is reacting. And the Na plus in gaseous form is now getting converted to Na plus in the aqueous form. Okay. So this is the free gaseous ion, the sodium ion. And to this, polar water molecules are reacting. So what will happen? The negative end of this water molecule will go and form the bond with the positive ion. The negative end of the water molecule will go and form the bond with the positive ion because unlike charges attract each other, right? So the negative only will go and form the bond with the positive. So unlike charges will attract each other and it will lead to this type of system. And this is the hydrated ion or the aqueous ion we can see. Okay. So water molecule has both end, right? Water is H2O. Oxygen is the negative end and hydrogen is the positive end. So negative means this particular negative end denotes the oxygen end and that oxygen end is going and forming the bond with the soul. And the ion is completely hydrated and now it is not called as a gaseous ion. Now it is an aqueous ion. Okay. Now here bond is forming or bond is breaking down. It is a bond formation process or bond breaking process. Can you tell me from the reactant to product what is happening? Bond is breaking. Oh my God. Between the two reactants I am asking. JNV Kurnul, between the two reactants I am asking. So initially we have only one ion, right? Yeah, it is a bond formation, right? So a new bond is formed between the cation and the negative end of the water molecule. So it is a bond formation process. Yes, very good, my dear. So only one student is watching from JNB Kurnul or the entire class is watching? May I know the name of the student who is watching behind? Individual, very good. May I know your name? May I know your name, please? Sri Lakshmi. Okay, okay, great. Sri Lakshmi, now it is clear for you, na? It is a bond formation. It is not bond breaking, okay? So now, if it is a bond formation process, yeah, very good, my dear. If it is a bond formation process, then what should be the sign of delta H of hydration? It should be negative or positive for bond formation. Bond formation. So the process will be exothermic. So all of you tell me whether the sign will be negative or positive. Bond formation. Bond formation means energy will be released. So it is an exothermic process. So delta H value will be negative. Very good, very good. All of you are doing great, you know. Very good. It is a negative. So it is minus 406 kilojoule per mole of energy is released for the formation of this bond. Okay. So this is all about hydration enthalpy. Now let me summarize the thermochemistry part which we have discussed so far. So initially in the thermochemistry we have discussed the enthalpy of combustion, and next it is atomization, third is bond enthalpy, and in that I have given you this formula to find out the bond enthalpy. Okay. Next is the lattice energy. And at last also we have studied the hydration energy, but lattice energy is more important. That's why I have kept that particular point alone in this slide. Okay. Lattice energy. Energy required to break 1 mole of an ionic compound in solid state to form the free gaseous ion is lattice energy. Clear? So I hope this is enough for today. Okay, we have discussed Hess law, thermochemical equation, and thermochemistry part in today's session. So do you have any doubt from today's class? So kindly give your answers in the poll which I am launching. Kindly give your answers in the poll which I am launching. So you can give your answers in the poll, and if you have any doubt, you can ask me in the chat box. If there is no doubt, once you answer the poll, you can leave and get ready for the next class. Thank you so much to all of you for listening to today's lecture. See you all in the next class. Okay? Till then, take care. Bye-bye. Thank you, Tanuja. Thank you, Sri Lakshmi. Bye. Bye. So others also try to give your answers. Others also try to give your answers in the poll which I have launched. Get ready for your next class.